Conservation of mass is a fundamental concept in chemistry. The previous video in the Chemistry Made Easy series, titled Introduction to Moles, showed us how the total mass of the reactants equals the total mass of the products. In this video we'll examine how the conservation of mass principle applies to a basic tool of chemical engineering, namely, mass balances, also referred to as material balances. Now let's get started. Chemical engineers often use mass balances to account for the quantities of every compound in multiple streams entering and exiting industrial chemical processes. These processes are called unit operations. The example we'll use here is the caustic refining process for crude soybean oil. We start by mapping out the process flow diagram as shown here. The process starts with a feed tank for the crude soybean oil. The main contaminants to be removed include free fatty acids and phospholipids, or gums. Crude unrefined soybean oil is pumped to a heat exchanger, where it is heated to the optimal reaction temperature. If the oil is too cold, the reaction will be too slow. If it's too hot, the caustic will break down the oil, resulting in excessive product losses. Next, a solution of sodium hydroxide and water is added to the crude feed. This solution typically consists of 13% sodium hydroxide and 87% water. This solution is also referred to as caustic soda, or more simply, caustic. The oil-caustic blend is then thoroughly mixed in a high-shear mixer. As the blend passes through the mixer, the caustic converts the free fatty acids into soaps. The soapy oil is then fed to a centrifuge. The centrifuge separates the soapy oil into two fractions. One fraction consists of a light, oleophilic, or oil-loving fraction. The other fraction consists of a heavy, hydrophilic, or water-loving fraction. The light fraction consists primarily of oil, along with a residual amount of soap and non-hydratable gums. The heavy fraction contains mostly hydratable gums, water, and soap with some residual oil, unreacted sodium hydroxide, and other polar material that was present in the crude feed. After we've mapped out the process flow diagram, we can draw a border around the process. This will help us identify the key input and output streams. To comply with the conservation of mass law, the total input mass must equal the total output mass, as illustrated here. Now let's take a look at the reaction between sodium hydroxide and free fatty acids, specifically oleic acid, which is the predominant free fatty acid in soybean oil. This reaction produces sodium oleate, or soap, and water. The molecular formulas for the reactants and products are shown here. When we add the molecular weights of the reactants, the sum equals the sum of the product's molecular weights. Therefore, our equation complies with the conservation of mass law. The reaction equation shows that 40 pounds of caustic are needed to neutralize 282 pounds of oleic acid. This ratio of 40 to 282 translates to 0.1418 pounds of caustic for 1 pound of oleic acid. But chemical reactions in industrial processes are rarely 100% efficient. So we must divide the theoretical, or stoichiometric amount of caustic by the percent efficiency, which in this example is 90% or 0.9, to give us the actual amount needed as shown here. The reaction equation also shows that 282 pounds of oleic acid are converted to 304 pounds of soap. This ratio of 304 to 282 translates to 1.078 pounds of soap produced from 1 pound of oleic acid. We can use this ratio to determine the amount of soap produced in our unit operation. Finally, the reaction equation also shows that 40 pounds of caustic produces 18 pounds of water. So we can use this relationship to determine the amount of water created by the reaction. Now it's time to quantify the individual components in the input and output streams. An analysis of the crude feed input stream reveals its composition. Phosphorus is a marker of phospholipids. It comprises about 1/30th of the mass of a phospholipid molecule. So, we multiply the phosphorus concentration by 30 to determine the average phospholipid concentration. The reaction equation showed us the mass ratio of caustic to oleic acid. So we can use this ratio to determine the concentration of caustic needed to convert the oleic acid to soap, in our example. Then we need to account for reaction inefficiency by adjusting the stoichiometric amount accordingly. From here we can determine the amount of water in the caustic solution, based on the typical caustic concentration of 13%. Now that we've quantified the concentration of the components in the caustic input stream, we can move on to the two output streams. The centrifuge's separation efficiency, which is 90% in this case, helps determine the compositions of the light and heavy streams. The heavy, water-loving stream contains highly polar components like hydrated gums, water, and soaps. So 90% of the incoming amounts of these highly polar components will wind up in the heavy stream, and the balance will go out in the light stream. Modern centrifuges have a higher separation efficiency for oil than for hydrated gums, water, and soaps. This helps minimize oil losses in the caustic refining step. This example specifies an oil loss of 0.05% in the heavy output stream. So, 0.05% of the total heavy stream will be oil. Finally, let's apply the molecular mass ratios from the reaction equation to determine the concentrations of soap and water formed. As shown here, our example produces 8,085 ppm of soap and 488 ppm of water. This is what the final mass balance looks like. It's based on 100 pounds of crude feed. The crude feed and caustic solution input streams consist of the components as specified earlier. The free fatty acids, or FFA, are converted to soaps according to molecular ratios in the reaction equation. And, as specified previously, 90% of the soaps, gums, and water go out in the heavy phase, and the remaining 10% go out in the light phase. The heavy fraction also includes excess unreacted caustic and other polar impurities that were present in the crude feed. Thanks for watching. I hope you found this short tutorial helpful. If you did, and would like to see similar content in the future, please like and subscribe. And if you have questions or specific topics that are of particular interest to you, please let me know in the comment section below. Also, don't forget to click the notifications bell so you don't miss out on future videos.